Could life have existed when the universe was just a cosmic toddler? This question reshapes our entire understanding of existence. By the end of this journey, you will discover how close life might have been to the very beginning of everything. We will explore how the first stars forged the ingredients for biology and whether dark matter itself could have powered the first living things. How does the possibility of a universe alive from its infancy change your sense of place in the cosmos? Before we can ask when life might have first sparked, we must first agree on what we are even looking for. Our only example of life is the biology we see here on Earth, a system based on carbon, water, and DNA. But is that the only possible form a living thing could take? A universal definition of life is one of science's greatest challenges. Most scientists describe life as a self-sustaining chemical system capable of undergoing Darwinian evolution. This focuses on the function, not the specific ingredients. It opens the door to life that might be built from entirely different chemistry, perhaps not even needing water or carbon. With this broader definition in mind, we can turn our attention to the stage itself, the universe in its earliest epochs. Our cosmic calendar begins with the Big Bang, an event that occurred roughly 13.8 billion years ago. For the first few hundred million years, the universe was a dark, featureless sea of simple gas. There were no stars, no galaxies, and crucially, no elements besides hydrogen, helium, and a trace of lithium. The complex atoms that make up our world, the carbon in our cells, the oxygen we breathe, the iron in our blood, did not yet exist. They had to be forged. This sets the boundaries of our investigation. We are searching for a window of time, a cosmic moment when the universe cooled enough for stable structures to form, and when the first generation of stars had lived and died, seeding the cosmos with the raw materials for planets and just maybe for life itself. This primordial darkness was not an empty void, but a simmering sea of potential. For millions of years, the universe existed in a state known as the cosmic dark ages. Picture a fog so deep and pervasive that not a single star pierced the gloom. The cosmos was a vast, silent expanse of hydrogen and helium gas, laced with the mysterious, unseen presence of dark matter. There were no landmarks, no sources of energy, no complex structures of any kind. It was a universe in waiting, a stage set for a performance that had not yet begun. The only force at work was gravity, patiently tugging at slight overdensities in the gas, drawing atoms together with imperceptible slowness. This was the quiet before the storm of creation. Then, after nearly 200 million years, a profound transition occurred. In the densest pockets of gas, gravity finally won its long battle. The first protostars ignited, and their fierce light began to burn away the cosmic fog. This was the epoch of first light, a dawn that fundamentally and forever altered the universe. These first stars were not like our sun. They were behemoths, hundreds of times more massive, burning ferociously hot and dying young in spectacular supernova explosions. It was within these stellar furnaces that the universe forged its first heavy elements. The carbon, oxygen, nitrogen, and iron that are the bedrock of all known life were literally born from the ashes of these first stars. Suddenly, the universe was no longer a simple soup of basic ingredients. It was now enriched, complex, and filled with new possibilities. The potential for planets, for chemistry, and for life had finally been seeded into the cosmos. These first stars, known as Population 3 stars, were titans of a forgotten age. They were colossal, many containing the mass of hundreds of suns. Their immense gravity created furnaces of unimaginable heat and pressure, burning through their hydrogen fuel in a cosmic blink. A star like our sun will shine for billions of years, but these giants lived fast and died young, their entire lifetimes lasting only a few million years. Their spectacular deaths were as important as their brilliant lives. When a population 3 star exhausted its fuel, its core collapsed, triggering a cataclysmic supernova explosion. This was not merely a star's death, it was the universe's first great act of creation. Within that unimaginable inferno, a nuclear alchemy occurred. The simple elements of the primordial universe, hydrogen and helium, were fused together under extreme conditions, forging for the first time the heavier elements essential for everything we know. Carbon, the backbone of all organic chemistry; oxygen, a vital component of water and air; iron, the element that carries oxygen in our blood. Every single atom of these substances in your body, in the ground beneath your feet, and in the planets throughout the cosmos was once forged in the heart of a long-dead star. These supernovae acted as cosmic seeders, hurling these newly created elements across interstellar space. They polluted the pristine hydrogen gas, enriching it with the raw materials for rocky planets, for complex molecules, and ultimately for life itself. The universe was no longer a simple place. It was now chemically rich and diverse, having acquired the very building blocks that would one day allow biology to emerge. So when did the clock for life truly start ticking? This changes everything we thought we knew about the cradle of life. The universe in its raw infancy may have offered a fleeting paradise. This is the core of the habitable epoch theory. After the first stars died and seeded the cosmos with heavy elements, the universe was a very different place. The residual heat from the Big Bang, what we now detect as the cosmic microwave background, was immensely stronger. Picture a warm bath of radiation filling all of space, a universal glow so intense it could heat the surface of a planet all on its own. This means a rocky world, even one drifting alone in the dark, far from any star, could have maintained liquid water on its surface. Its warmth would not come from a nearby sun, but from the entire cosmos. The energy of creation itself would be its power source. This creates a stunning possibility. A mere 10 to 20 million years after the Big Bang, the entire universe could have been, for a brief cosmic moment, a potential incubator for life. Any planet with a rocky surface and a sufficient atmosphere could have possessed the one ingredient we consider essential for biology: liquid water. This universal habitability window would have been incredibly short. As the universe expanded, this background radiation cooled and faded, its warming effect diminishing until it was no longer enough to sustain liquid water on lonely worlds. But for that brief epoch, the conditions for life might not have been a rare anomaly around special stars. They could have been everywhere. The question then becomes not if a planet was in the right place, but if any planets could have even formed that quickly. This brings us to one of the most profound and speculative possibilities of all. What if the first life did not need starlight or the cosmic background glow for energy? What if it tapped into the universe's most abundant yet most mysterious substance, dark matter? We still do not know what dark matter is, but we know its gravitational pull holds galaxies together. It is everywhere, a ghostly sea of particles that vastly outnumbers the ordinary atoms we are made of. In the early universe, this dark matter was far denser, concentrated into a tighter web. Some theoretical physicists have proposed a startling idea. On a free-floating planet, a rogue world drifting in the emptiness between stars, the planet's gravity could have continuously pulled a stream of dark matter particles into its core. If certain types of dark matter particles can interact with each other, they could annihilate upon contact, releasing a steady, gentle trickle of energy as heat. This process would be like a slow-burning nuclear reactor, buried deep within the planet, powered not by uranium, but by the invisible fabric of the cosmos itself. A world like this would have no sun. Its surface would be a frozen, airless wasteland, but deep underground, warmed by this dark matter heart, vast subsurface oceans could remain liquid for billions of years. In those sunless abysses, the heat from annihilating dark matter could power the same kind of geothermal vents and chemical reactions that support entire ecosystems on Earth's ocean floors. Life would not look to the sky for energy. It would draw its sustenance from the planet's own internal dark engine. This is for now a theory on the farthest edge of cosmology. But it expands the concept of a habitable zone from a narrow band around a star to include any world, anywhere, with a strong enough gravitational pull to concentrate this dark fuel. It suggests that the potential for life could have been woven into the very architecture of the universe from the start, a silent, hidden possibility waiting in the dark. This cosmic seeding leads us to a powerful and ancient idea, panspermia. If life could gain a foothold on just one of those early, warm worlds, what would stop it from spreading? The theory of panspermia suggests that life does not need to originate independently on every single planet. Instead, it can be transported, hitching a ride on rocks blasted into space by asteroid impacts or volcanic eruptions. Imagine a massive asteroid slamming into a young, life-bearing world. The impact could catapult fragments of its crust containing hardy microorganisms out into the void. These microscopic travelers, encased within their rocky spaceships, could then drift for millions of years through the emptiness of interstellar space. The early universe, still dense with young solar systems and rogue planets, might have made such a journey far more likely than it is today. A microbe frozen in stasis within a protective shell of rock could, in theory, survive the vacuum, the cold, and even radiation for an astonishingly long time. If such a rock were eventually captured by the gravity of another young world, falling through its atmosphere to land in a warm, welcoming ocean, the seed of life could be planted anew. This process would transform life from a rare, local event into a cosmic phenomenon, a chain reaction of biological inheritance that could leap from star system to star system. But could any organism possibly survive the violent ejection, the long journey, and the fiery re-entry? We know that certain extremophile bacteria on Earth are incredibly resilient. They can withstand extreme temperatures, pressures, and doses of radiation that would be instantly lethal to most other life forms. Encased deep within a sizable rock, these tiny pioneers could be shielded from the worst of space's hazards. The real challenge in the early universe would have been the intense radiation from those first massive stars and their frequent, violent supernova. A journey lasting millions of years through such a hostile environment would be the ultimate test of endurance. Yet, if just one microbe in a billion survived such an odyssey, it could have been enough to sow the galaxy with life's potential. This idea dramatically accelerates the possible timeline for life's spread. If life emerged on just one world during that brief, universally warm epoch, it might not have remained there for long. The very impacts that threatened to sterilize that world could have also been its salvation, scattering its biological legacy far and wide. The universe, in its youth, could have been engaged in a constant, silent exchange of living cargo, turning isolated pockets of biology into an interconnected web of life. So the stage was set with the universe newly enriched and potentially warm. But could planets, the very platforms for life, have assembled in time to take advantage of that brief cosmic spring? The search for the first planets pushes our telescopes to their absolute limits. We now have compelling evidence that planet formation is not a leisurely, modern-day process. It is a race that began at the dawn of time. Astronomers have discovered white dwarf stars that are among the oldest in our galaxy. These ancient stellar embers are slowly cooling, and by analyzing their light, scientists can detect the chemical fingerprints of rocky, planetary material that has fallen into them. The stunning conclusion is that this polluting debris shows signs of having been part of fully formed rocky planets. The timeline is breathtaking. These planetary systems appear to have existed when the universe was less than 1 billion years old. This means the first solid worlds, the first landscapes under alien skies, could have emerged a mere few 100 million years after the Big Bang. Think of the cosmic calendar, where all 13.8 billion years of the universe are compressed into a single year. The Big Bang is at the stroke of midnight on January 1st. On this scale, the evidence suggests that the first planets could have formed by early to mid-January. Life on Earth did not appear until late September. This radically compresses the timeline for life's potential debut. The building blocks were there, the warmth was there, and now we know the real estate was there too. These primordial planets would have been utterly alien worlds, orbiting short-lived, furious stars. Their surfaces would have been bombarded by intense radiation, and their geology forged from a simpler, purer mix of elements. But they would have been solid ground. They could have held atmospheres, and most importantly, they could have possessed liquid water, either on their surfaces from the cosmic background heat or in vast subterranean oceans. The confluence of these factors is staggering. The universe did not wait for ideal conditions to start building the homes for life. It started almost immediately, turning the possibility of life in the cosmic dawn from a wild speculation into a testable and increasingly plausible hypothesis. The concept of a habitable zone extends far beyond the orbit of a single star. Entire galaxies have regions of life and death, a galactic habitable zone where the conditions are just right for complex biology to emerge. In the tumultuous early universe, not all neighborhoods were created equal. The chaotic hearts of nascent galaxies were incredibly dangerous places. Here, supermassive black holes were actively feeding, unleashing torrents of deadly radiation. Stars were packed tightly together, their gravitational dances frequently disrupting budding planetary systems and triggering waves of sterilizing supernova. Any fledgling life in this central metropolis would have been constantly threatened. Conversely, the sparse outer rims of these early galaxies presented a different kind of challenge. These regions were metal-poor, meaning they contained very few of the heavy elements forged by the first stars. Without a rich supply of carbon, oxygen, and iron, the formation of rocky planets like Earth becomes nearly impossible. You might have vast clouds of primordial gas, but they lack the cosmic dust and grit required to build solid worlds. This creates a galactic sweet spot, a ring within the sprawling disk of a galaxy where stability and chemistry align. Far enough from the violent core to avoid constant catastrophe, yet enriched enough with heavy elements to form terrestrial planets. In this annular haven, a star could form with a stable planetary system, bathing its worlds in steady light for billions of years. It is within this galactic suburbia, this calm and chemically rich spiral arm, that the universe's first experiment with life was most likely to succeed. This reframes our search, shifting our gaze from any random planet to those orbiting the right kind of star, in the right part of the right galaxy, at the right time in cosmic history. This cosmic silence forces us to confront a haunting possibility. We look out at a vast and seemingly empty galaxy and ask a simple, profound question. Where is everybody? This is the heart of the Fermi paradox. If the universe is so old and so large, teeming with billions of planets, why have we encountered no evidence of other civilizations? One compelling answer is the Great Filter hypothesis. This idea suggests that the evolution of life from its simplest form to a spacefaring civilization requires passing through a series of incredibly difficult, perhaps nearly impossible steps. One of these steps acts as a cosmic bottleneck, a barrier so formidable that it effectively filters out almost all potential life. If life truly did spark into existence during the universe's first chapters, its early emergence might not be a sign of its success, but a clue to its ultimate fate. That initial warm epoch was incredibly brief. The cosmic background radiation faded quickly, leaving any life that depended on it in a desperate race against time. A world warmed by the entire cosmos would, in just a few million years, find its oceans freezing solid, its atmosphere collapsing into ice. Any life that had begun in that fleeting paradise would have been suddenly thrust into a deep freeze, a planet-sized snowball drifting in the eternal night. This could have been a universal great filter. Life may have arisen on countless worlds during that brief springtime, only to be almost universally extinguished when the cosmic winter arrived. The universe itself provided the cradle, and then it just as swiftly took it away. The transition from simple, single-celled life to complex, intelligent organisms is another potential filter of staggering difficulty. On Earth, this leap took over 3 billion years. The early universe was a far more violent place, with frequent gamma-ray bursts and supernovas sterilizing entire regions of galaxies. A promising biosphere could be wiped out in an instant by a random stellar explosion, resetting the evolutionary clock to zero over and over again. Perhaps the filter lies even later in the technological phase itself. Maybe any civilization that reaches a certain level of advancement inevitably discovers a technology, perhaps in particle physics or artificial intelligence, that leads to its own destruction. The silence we hear today would then be the echo of countless civilizations that burned brightly for a moment, only to flicker out. If life arose extremely early, it had a head start of billions of years. The fact that we see no evidence of its lasting legacy suggests that something, somewhere along the line, stopped it. This is a humbling thought. Our own existence might mean we have already slipped through this cosmic filter, that the greatest challenges are behind us. Or it could mean the most difficult test still lies in our future, a challenge that has silenced every other voice in the cosmos. The violent conditions of the early universe were not an absolute barrier to life, but a filter demanding incredible resilience. To understand what could have survived, we look to Earth's own survivors, organisms that thrive in places once thought utterly lifeless. These are the extremophiles, and they offer a stunning blueprint for what the first cosmic life might have been. In the scalding, acidic waters of hydrothermal vents, where temperatures can melt lead, entire ecosystems flourish, powered not by the sun but by chemical energy from the Earth's core. Microbes known as thermophiles do not merely endure this heat, they require it. In the deep, frozen darkness of Antarctic ice, another type of microbe, a psychrophile, makes its home, its biological processes adapted to function in perpetual cold. Then there are the radiotrophic fungi discovered thriving inside the wreckage of the Chernobyl nuclear reactor, using the pigment melanin to literally feed on radiation, transforming a lethal energy source into food. These are not fragile beings, they are the ultimate tough guys of the biological world. If life emerged on one of those first irradiated planets, it would have had to resemble these hardy pioneers. A delicate, sun-dependent organism would have been instantly erased by a nearby supernova's gamma-ray burst or the relentless ultraviolet glare of a massive young star. But a radiotrophic microbe, similar to our Chernobyl fungi, might have not only survived but thrived in that high-energy environment. A thermophile buried deep in a planet's crust, insulated from surface cataclysms and drawing energy from geothermal heat or even dark matter annihilations, could have persisted for eons completely independent of a star. These life forms redefine habitability. They show us that life is not a rare flame that needs perfect shelter, but a tenacious spark that can take hold in the most astonishingly hostile corners of reality. The first life in the cosmos was likely not a gentle, green thing basking in sunlight. It was probably a microscopic, rugged individualist hunkered down in the rocks, feeding on radiation or geothermal vents, waiting out the universe's turbulent childhood. This shifts our entire perspective on where and how we should search for life beyond Earth, pointing our gaze away from placid, Earth-like worlds and toward the most extreme and ancient environments the cosmos has to offer. These rugged first organisms, however, had to come from somewhere. life does not simply appear, it emerges from a long and intricate chemical dance. The transition from non-living matter to the first living cell is known as abiogenesis, and understanding its first steps is key to knowing if it could have happened in the cosmic dawn. Scientists searching for the origin of life often focus on a molecule called RNA, ribonucleic acid. In all life today, RNA is a crucial messenger, carrying instructions from DNA to guide the construction of proteins. But it can do much more. Some forms of RNA can act as tiny enzymes, catalyzing chemical reactions all by themselves. This dual talent as both an information carrier and a chemical tool has led to a compelling idea called the RNA world hypothesis. The theory suggests that before DNA or proteins existed, the first life was based entirely on self-replicating RNA molecules. A single strand of RNA that could copy itself would be the most fundamental form of life imaginable, a molecule that could store information, perform work, and make more of itself. This is the probable starting gun for biology, but how could such a complex molecule simply form from the simple chemistry of the early universe? The building blocks of RNA, known as nucleotides, are themselves intricate structures. For decades, their spontaneous formation in a primordial soup seemed like a huge obstacle. Then, experiments revealed a stunning possibility. These nucleotides might not have needed a calm, warm pond. They could have been forged in the most hostile environments imaginable. When scientists simulate the conditions of interstellar space in a laboratory, exposing simple gases like methane, ammonia, and water to the harsh energy of ultraviolet radiation or electrical discharges, they find that these basic ingredients can combine to form nucleobases, the informational parts of RNA. Even more remarkably, when a rocky, clay-rich surface is added to the mix, these nucleobases can link up with sugar and phosphate molecules, assembling into the complete nucleotides that form RNA chains. This suggests that the very first steps toward life, the creation of its fundamental building blocks, could have occurred not on a planet, but in the vast molecular clouds of deep space on the surfaces of dust grains and icy comets. These probiotic ingredients could have been raining down on young planets from the very beginning, delivered by comets and asteroids as cosmic care packages. The universe, it seems, might have been a giant chemistry set, manufacturing the pieces of life long before any planet was truly ready to assemble them. So the chemistry was possible, but could it have happened fast enough? The early universe, despite its violence, offered one significant advantage: a much higher density of carbon and other essential elements immediately after the first stars died. This rich, concentrated chemical soup, combined with the universal warmth of the cosmic background radiation, could have made the assembly of these first RNA molecules not just possible but probable. The leap from a self-replicating molecule to a primitive cell is vast, but the foundation was laid in the fires of the first stars and the frozen voids of interstellar space. The stage was not just set with planets and energy, but stocked with the very chemicals needed for the play to begin. The universe's first spring was a paradise fraught with peril. For any nascent life, survival was a constant gamble against forces of unimaginable fury. The very stars that forged the elements of life were also its most prolific executioners. Gamma-ray bursts stand as perhaps the most destructive phenomenon in the cosmos. When some of those first monstrous stars reached the end of their lives, they did not simply explode in a supernova. They collapsed into hypernova, focusing their dying energy into two narrow, opposing beams of radiation so intense they could outshine an entire galaxy for a brief, terrifying moment. If a planet, even 1 light-years away, happened to lie in the path of such a beam, the consequences were absolute sterilization. The gamma rays would rip apart its atmosphere, destroying the protective ozone layer and bathing the surface in a flood of lethal ultraviolet radiation. Any life not shielded by kilometers of rock or ice would have its cellular machinery shredded in an instant. These events were not rare curiosities in the crowded, violent early universe. They were likely a regular, apocalyptic occurrence. Beyond these singular catastrophes, the background environment itself was a persistent threat. The first stars emitted a ferocious amount of ultraviolet light, a constant, searing glare that would have broken down complex organic molecules on any exposed surface. Planetary systems were also chaotic construction zones, subject to a relentless hailstorm of asteroids and comets. The late heavy bombardment that pockmarked our own moon was a gentle rain compared to the constant pummeling experienced by worlds in a young solar system. Each large impact released energy equivalent to millions of nuclear bombs, flash heating the planet's surface and vaporizing oceans. For a fledgling biosphere, this was a cycle of creation and destruction. The same impacts that delivered water and the building blocks of life could just as easily scour that life from existence. So, what were the odds? Could any life possibly endure this gauntlet of fire and ice? The probability seems vanishingly small when viewed from the surface, but life as we know it is stubbornly tenacious. It would not have been basking on a beach. The only conceivable survivors would have been deep underground or deep underwater, in subsurface aquifers or at the dark, insulated depths of an ocean. There, protected by miles of rock and water, a community of extremophile microbes could have been shielded from the surface apocalypse. Even a gamma-ray burst's secondary effects, while devastating to the surface, would have been muted to a gentle rumble in the deep crust. The real threat to such hidden life would not have been the initial blast, but the long-term climatic collapse that followed as the damaged atmosphere struggled to recover. Survival in the cosmic dawn was not about avoiding catastrophe, but about finding a refuge deep enough to wait it out. The universe was testing life from its very first breath, demanding resilience as the price of existence. Finding evidence of such ancient life requires looking for ghosts in the cosmic machine. We must search for faint chemical whispers left behind by biology that flourished over 13 billion years ago. The key lies not in finding the microbes themselves, but in detecting their lasting impact on a world. On Earth, life has completely reshaped our atmosphere. The abundant oxygen we breathe is a direct product of photosynthesis, a gas that would quickly vanish without living organisms constantly replenishing it. Similarly, methane produced by microbes creates a chemical imbalance that would not persist in a sterile, geological environment. These are biosignatures, atmospheric fingerprints that scream the presence of life. To find these signatures from the universe's dawn, we must turn our gaze to the oldest stars in the cosmos, the ancient red dwarfs and diminutive suns that formed from the primordial ashes of the first stellar generations. Orbiting these venerable stars are rocky planets that have existed for nearly the entire history of time. If life ever gained a foothold on one of these worlds during that early warm epoch, and if it managed to persist or leave a detectable mark, its atmospheric ghost might still be present. The next generation of colossal telescopes, like the James Webb Space Telescope and the future Extremely Large Telescope, are being designed to do exactly this. They will act as cosmic time machines by capturing the faint starlight that filters through the atmosphere of a distant exoplanet. They can split that light into a spectrum, revealing the unique chemical barcode of the gases present. Imagine a world so old that its light has been traveling for over 13 billion years to reach us. A telescope intercepts that ancient photon and, within its data, finds an unexpected spike at the wavelength for oxygen, alongside a curious abundance of methane. This specific combination, this chemical paradox that should not exist naturally for long, would be our strongest possible hint of ancient biology. It would be a signal that, once upon a time, in the universe's fiery youth, a planet was not just a rock but a living world. The discovery of such a biosignature around an ancient star would rewrite our story. It would mean life is not a latecomer to the universe, but a foundational part of its character, a phenomenon that began when the cosmos itself was still young. This staggering possibility of a living universe in its infancy forces a profound question about the nature of reality itself. Why do the fundamental rules of our cosmos seem so perfectly arranged for our existence? The force of gravity, the strength of the nuclear forces, the mass of an electron, each of these constants appears to be precisely tuned. If gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, matter would never have clumped together to form stars and galaxies. This is the puzzle of fine-tuning, a cosmic coincidence that seems too perfect to be an accident. It is as if the universe knew we were coming, setting its dials to exactly the right values to allow for planets, chemistry, and life. This line of reasoning leads directly to the anthropic principle, a philosophical idea with a simple yet mind-bending premise. The universe must be compatible with conscious life because we are here to observe it. We do not live in a universe hostile to biology because if it were, we would not exist to ponder the question. This is not an explanation so much as a statement of a selection effect. We find ourselves in a universe capable of producing us, so we should not be surprised that its laws are favorable. But does this principle simply state the obvious, or does it point to something deeper? If life could emerge in the first few 100 million years, it suggests that the conditions for biology are not a fragile, unlikely fluke. They might be a fundamental output of a universe built with the right initial recipe. The constants were not just set to allow for life eventually, they were set to allow for life almost immediately, as soon as the first stars could forge the necessary elements. This transforms the narrative from one of lucky chance to one of cosmic inevitability. In such a view, life is not a rare accident in a vast, indifferent cosmos. It is a fundamental feature of a universe whose very laws are biased toward complexity and consciousness. The potential for early life becomes a powerful data point, suggesting that the emergence of biology is not an afterthought, but written into the fabric of space-time from the very first moment. This fixation on carbon and water might be our greatest blind spot. To truly grasp the potential for life in the cosmic dawn, we must let go of Earth's blueprint and consider the universe's full chemical imagination. Carbon is the backbone of our biology for excellent reasons. It has a unique talent for forming 4 strong, stable bonds with other atoms, allowing it to construct the long, complex chains and rings that become proteins, DNA, and the very structures of our cells. It is the ultimate Lego brick of chemistry, but is it the only brick? Directly beneath carbon on the periodic table sits silicon. Like carbon, silicon can form 4 bonds. It is one of the most abundant elements in the universe, a primary component of sand and rock. A strong case can be made for a silicon-based biology. Where carbon combines with oxygen to make carbon dioxide, a gas we exhale, silicon combines with oxygen to make silica, the mineral that forms quartz. Imagine a life form whose bones are not calcium but crystalline silica structures, and whose genetic material is not a carbon-based double helix, but a complex, shimmering chain of silicon and oxygen. Its metabolism would be utterly alien, perhaps processing sulfur or metals where we process sugars. The early universe, still rich with unoxidized silicon from supernova ejecta, could have been a perfect nursery for such exotic chemistries. The solvent for this life is another question. We view water as essential because it dissolves nutrients, facilitates chemical reactions, and remains liquid across a wide temperature range. But what if a world was too cold for water or never had any to begin with? Ammonia is a compelling alternative. Liquid ammonia is an excellent solvent for a vast range of chemical processes. It remains liquid at much colder temperatures than water, flowing freely on worlds far from their star's warmth. An ammonia-based ocean, swirling beneath a frozen crust of water ice, could host an entire ecosystem of creatures with biochemistry running at a slower, more deliberate pace. Their cells would be structured not with lipids but with other molecules stable in that frigid, alkaline environment. These are not mere fantasies. They are logical extrapolations of chemistry under different cosmic conditions. The early universe was a place of extreme temperatures and exotic environments that no longer exist today. This opens the door to life forms that utilized energy sources now faded into the background of the cosmos. In that first warm epoch, a life form might have evolved to directly metabolize the intense infrared radiation of the cosmic microwave background itself, treating the entire universe's residual heat as its sun. Or perhaps on a world with a powerful magnetic field, organisms learned to feed on the auroral currents dancing in its atmosphere, drawing power from the planet's interaction with its star. The possibilities are as vast as the elements forged in those first stellar explosions. By clinging only to the biology we know, we risk building a detector that is deaf to the most common songs of life in the universe. The first life may not have been a primitive version of us, but something entirely different, a form perfectly adapted to a universe we can now only reconstruct in our theories. Our timeline begins not with a bang, but with a question mark. The Planck epoch is the universe's first fleeting moment, a span of time so short it defies imagination, where the very laws of physics as we know them did not yet exist. From this sea of pure potential, the universe inflated in a spectacular, exponential growth spurt, smoothing and stretching the fabric of spacetime itself. Then, after just 380,000 years, a pivotal event occurred: recombination. The hot, dense plasma of particles cooled just enough for electrons to be captured by protons, forming the first stable atoms, almost entirely hydrogen and helium. In that instant, the universe became transparent, releasing the flash of light we now detect as the cosmic microwave background. This was the universe's first baby picture. For nearly 200 million years, darkness reigned during the cosmic dark ages, a quiet era where gravity alone worked to pull matter into denser clouds. Then a cosmic dawn broke. The first stars, the colossal population 3 stars, ignited, their fierce ultraviolet light burning away the primordial fog and flooding the cosmos with the first starlight. Their lives were brilliant and short. Within just a few million years, they died in titanic supernova, and in their deaths, they forged and scattered the first heavy elements, the carbon, oxygen, and iron essential for life. This stellar alchemy changed everything. The universe was no longer pristine, it was now chemically enriched, and here is where the timeline accelerates beyond all expectation. Within a mere few 100 million years after the Big Bang, the first rocky planets began to coalesce from this newly enriched dust. We have evidence that planetary systems were already in place when the universe was only around 1 billion years old. This means the stage was set with breathtaking speed. The cosmic background radiation was still intensely warm, potentially providing universal heating. The building blocks of RNA were likely already forming in interstellar space. So, when could life have first sparked? The most optimistic theories point to a window just 10 to 20 million years after the Big Bang. On a cosmic calendar that compresses the entire history of the universe into a single year, the Big Bang occurs at the first instant of January 1st. By this scale, the first stars lit up before dawn on January 1st, the first planets formed by mid-morning, and the very first life could have emerged by the afternoon of that very first day. Life on Earth, by comparison, does not appear until late September. This compressed timeline is a profound revelation. It suggests that the universe did not dawdle in its creative potential. As soon as the most basic ingredients were available, the cosmos began assembling them into structures of ever-increasing complexity, rushing from a featureless fireball to a potentially living universe in what amounts to a cosmic heartbeat. This silent search for ancient ghosts now has its most powerful listener. The James Webb Space Telescope is not just another observatory, it is a time machine engineered to peer into the cosmic dawn. Its primary mission is to capture the faint, stretched light from the very first stars and galaxies, light that has been traveling for over 13 billion years. To see that far back, you cannot use ordinary visible light. The expansion of the universe has shifted that ancient starlight into the infrared part of the spectrum, like a cosmic echo fading into a lower register. Webb's giant golden mirror and its supercooled instruments are designed to be exquisitely sensitive to this infrared glow, allowing it to see details of that early era that were previously just theoretical whispers. But its power goes far beyond simply taking pictures of infant galaxies. Webb can perform a trick of almost magical precision: transmission spectroscopy. When a distant planet passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases in that atmosphere absorb specific wavelengths of light, leaving behind a unique chemical barcode in the starlight. By analyzing this barcode, Webb can, for the first time, determine the atmospheric composition of small, rocky worlds orbiting the oldest stars in our galaxy. It is hunting for those biosignatures, the telltale chemical imbalances like oxygen and methane coexisting, that would suggest a living world. Every time Webb points its mirror at one of these ancient red dwarf stars, it is conducting an archaeological dig on a cosmic scale. It is sifting through the atmospheric ghosts of planets that have existed since the universe was in its youth, searching for a single, profound signal that life's story began not with a slow, hesitant prologue, but with a dramatic opening act written in the first pages of cosmic history. These simulations are vast digital universes born from lines of code. Cosmologists build them by encoding the fundamental laws of physics, the nuclear reactions inside stars, and the complex chemistry of molecular clouds. They start with the initial conditions just after the Big Bang, a hot, dense soup of particles, and then hit the virtual fast-forward button. The computer calculates how gravity pulls matter into the first clumps, how those clumps collapse into the first stars, and how those stars explode to seed space with new elements. It is a cosmic experiment run 1,000 times over, each time tweaking a single variable to see what happens. What if the first stars were smaller? What if dark matter interacted more strongly? The simulation reveals the consequences, painting a dynamic picture of how planets could coalesce from the ashes of that first stellar generation. But the models go deeper than just astrophysics. Astrobiologists inject the rules of chemistry and biology into these virtual worlds. They program in the known reactions that create amino acids and the components of RNA on icy dust grains or in volcanic pools. Then they watch, they observe how these probiotic molecules behave in the simulated environments of early planets. Does the universal background radiation provide enough steady warmth to keep water liquid for a meaningful amount of time? Do the frequent asteroid impacts deliver enough organic material, or do they sterilize the surface too often? The simulation becomes a laboratory for testing the most critical question of all, the probability of that final leap from complex chemistry to a self-replicating system. It tests the resilience of life itself. For instance, one simulation might show that on a rogue planet warmed by dark matter, the subsurface oceans remain stable for billions of years, providing a perfect protected incubator. Another might reveal that the ultraviolet radiation from a nearby massive star would break down any complex molecules on a world's surface in just a few thousand years, making the emergence of life there nearly impossible unless it was buried deep underground. These are not just abstract calculations, they are stories of potential worlds told by a machine. The power of this approach is its ability to explore countless dead ends and rare successes without ever leaving Earth. We cannot travel back in time to visit the cosmic dawn, but we can build a digital twin of it, a proving ground for our grandest theories about life's first, faint whisper in the cosmos. This perspective transforms our place in the cosmic story from a lucky accident to a potential inevitability. If life ignited so readily in the universe's turbulent dawn, then biology might be a common, even fundamental, feature of cosmic evolution. The silence we perceive, the great quiet of the Fermi paradox, then becomes even more profound and puzzling. A universe that is inherently biophilic, one that quickly fills with living worlds, should logically be teeming with intelligence. So where is everyone? The answer may lie not in the rarity of life's start, but in the immense challenges of its long-term survival. The same violent cosmic environment that forged the first building blocks also presented constant existential threats. Gamma-ray bursts, stellar cataclysms, and the rapid cooling of the cosmic background would have acted as relentless filters. This suggests a sobering possibility. The Great Filter, the bottleneck that prevents life from progressing to a spacefaring civilization, might not be behind us but directly ahead. Our own technological adolescence, with its risks of self-annihilation or ecological collapse, could be the very challenge that has silenced countless other worlds. This knowledge reframes our search for extraterrestrial intelligence. We should not only listen for deliberate signals, but also scour the atmospheres of the most ancient, stable stars for the chemical ghosts of civilizations that endured. Finding a biosignature on a planet orbiting a 10-billion-year-old star would be a monumental discovery, proving that a species can navigate the perils of its own technology and achieve longevity. It would offer a beacon of hope, a sign that the Great Filter is not insurmountable. For our own species, this understanding is a powerful call to wisdom. It tells us that our most critical task is not merely to find other life, but to ensure our own survival long enough to join a potential cosmic community. The story of early life is not just an ancient history lesson, it is a mirror held up to our future. It suggests that the universe is primed for life, but that the ultimate test is whether life can become wise enough to steward its own destiny among the stars. We are cosmic archaeologists sifting through the remnants of a vanished age. Our fossil record is not buried in stone, but written in the ancient light of long-dead stars and the cold echo of creation itself. The oldest stars in our galaxy are living fossils. They formed from the pristine ashes of the very first supernova, and their atmospheres preserve a perfect chemical snapshot of that primordial era. By analyzing the faint starlight from these ancient suns, we can read the recipe of the early cosmos, measuring the exact amounts of carbon, oxygen, and iron available when the first planets were coalescing. This tells us if the universe's chemistry was rich enough, early enough to support the intricate dance of biology. Then there is the ultimate relic, the cosmic microwave background. This is not just a baby picture, it is a detailed map of the universe's infancy, a fossil imprint of the density variations that would one day become galaxies. By studying its subtle imperfections, we can understand the thermal environment of that early epoch, calculating just how warm the universe was and for how long that cosmic warmth could have cradled liquid water on lonely worlds. Even the vast, diffuse clouds of gas that drift between galaxies hold clues. These are time capsules, pockets of space that have remained almost untouched by later generations of stars. Their chemical composition, revealed by the light of distant quasars shining through them, tells us about the universal distribution of those first heavy elements. Was the enrichment patchy, leaving vast deserts devoid of the ingredients for life? Or was it a widespread drizzle, seeding virtually every corner of the cosmos with potential? Every piece of this evidence is a fragment of a cosmic puzzle. When we combine the stellar fossils, the background echo, and the pristine gas clouds, we are not just collecting data. We are reconstructing the environment of a lost world, building a profile of a crime scene 13 billion years cold, searching for the faint, chemical fingerprints left by a universe that may have been alive in its youth. These quantum processes are not confined to the distant past, they operate within us right now. One of the great puzzles of life's origin is how the first complex molecules, like the components of RNA, could have formed with such efficiency. The reactions needed to build them often face significant energy barriers, like a hill too steep for chemicals to climb. This is where the strange rules of the quantum world intervene. Quantum tunneling allows a particle to perform a kind of magic, vanishing on one side of an energy barrier and reappearing on the other without ever going over the top. It is as if the molecule simply winks out of existence and then winks back into existence on the other side of the obstacle. This is not a theory. We see it happening inside our own cells, where enzymes use quantum tunneling to speed up vital reactions by factors of millions or more. In the dense, warm conditions of the early universe, this quantum cheat code could have been turbocharged. With matter packed more tightly and energies running high, the probability of these tunneled reactions could have been vastly greater, turning a slow, improbable chemical crawl into a rapid, prolific assembly line for life's building blocks. Perhaps the first self-replicating molecule did not slowly stumble into existence, but quantum leaped there. This introduces a breathtaking possibility. The very laws that govern the smallest particles may have actively biased the universe toward the emergence of life, guiding chemistry along a faster, more certain path. Another quantum phenomenon, known as coherence, adds another layer to this story. In our warm, wet world, quantum coherence is a fragile thing, typically lasting only fleeting instants before being disrupted by the jostling of other molecules. This is the quantum version of a perfectly synchronized choir that quickly descends into chaotic noise. But what if the early universe provided a quieter stage? In the cold, isolated environment of interstellar space, on the surface of a dust grain deep within a molecular cloud, quantum states could have remained coherent for much longer periods. This extended coherence could have allowed for a form of quantum computation, where a molecule explores multiple chemical pathways simultaneously, inevitably finding the most efficient route to complexity. It is a speculative but powerful idea. The first steps toward life might not have been a series of random, accidental collisions, but a directed search, orchestrated by the fundamental quantum properties of matter itself. The universe, in its first moments of chemical creativity, may have been conducting a quantum-assisted experiment, one whose successful result was us, and perhaps countless other forms of life scattered across the cosmos. For all its breathtaking scope, this vision of an ancient, living universe faces formidable scientific skepticism. The leap from cosmic chemistry to a living cell is immense, and many researchers question whether it could have happened in the chaotic infancy of everything. The first major hurdle is the availability of the very building blocks. While the first stars forged carbon and oxygen, they produced only a limited palette of elements. The universe was still desperately poor in the heavier atoms like phosphorus and molybdenum, which are crucial for the enzymes that power all known life. Could a functional biochemistry even exist without this full suite of elements? The early cosmic chemistry set may have been missing several key ingredients. Then there is the issue of time. On Earth, the journey from non-living molecules to the first simple cells took hundreds of millions of years, and that was on a stable, resource-rich planet. In the violent early universe, the window of universal warmth was open for a mere 10 million years, a cosmic blink. Could the incredibly complex processes of abiogenesis, the random assembly of self-replicating molecules, really have occurred so rapidly? The statistical odds seem vanishingly small, like shaking a box of Scrabble tiles and having them land as a perfect sonnet. Compounding this is the sheer hostility of the environment. The early cosmos was flooded with ultraviolet radiation from massive stars, and space was frequently torn by gamma-ray bursts. These events would have acted like a universal sterilizing lamp, breaking apart complex organic molecules faster than they could form. A fledgling chain of RNA, the hypothetical first genetic molecule, would have had its chemical bonds shattered in an instant by a stray photon. For life to begin, it would have needed a refuge of almost perfect isolation, a place shielded from the very energy that filled the universe. The counterargument is not that life is impossible, but that its emergence requires a rare convergence of stability, resource abundance, and time, conditions that the rambunctious early universe may have been uniquely unsuited to provide. This skepticism is a vital check on our cosmic dreams, forcing us to ask not just if something is possible, but if it is probable in the face of a universe designed to test its own creations to their breaking point. The hunt for our cosmic origins is accelerating, armed with a new generation of tools that will transform speculation into knowledge. On the horizon are observatories of such staggering power, they will allow us to stare directly into the atmospheres of Earth-sized worlds orbiting the oldest stars. The Habitable Worlds Observatory is a planned space telescope designed with one primary goal: to find and analyze planets that could support life. Imagine an instrument capable of blocking out the overwhelming glare of a distant star, allowing it to see the faint, reflected light of a small, rocky planet. It would not just detect these worlds, it would read their atmospheric composition with a precision far beyond anything we have today, searching for those telltale biosignatures like oxygen and methane in combinations that shout the presence of biology. This is the logical next step, a dedicated mission to find the chemical ghosts of ancient life. On the ground, the scale of ambition is equally immense. Telescopes like the extremely large telescope, with a mirror nearly the size of a football field, are rising from mountaintops. These colossal instruments will gather so much light they can study the formation of the very first planetary systems in unprecedented detail, watching as dust and gas coalesce into new worlds around infant stars. They will act as time machines, showing us the processes that built planets in the early universe, allowing us to understand how common our own solar system's architecture truly is. But to move from detecting atmospheric gases to confirming life, we may need to get much, much closer. This is the realm of visionary concepts like interstellar probes. Projects like Breakthrough Starshot aim to send tiny, lightweight spacecraft to our nearest stellar neighbors, propelled by powerful Earth-based lasers. These nanocraft, traveling at a significant fraction of the speed of light, could fly through the alien solar system of Proxima Centauri within a human lifetime, beaming back images and data of its potentially habitable planet. While this technology is in its infancy, it represents a fundamental shift from passive observation to active exploration. It raises the stunning possibility that within a century we might have a family portrait of another world, a grainy image that reveals continents, oceans, and perhaps even the unmistakable patterns of a biosphere. The ultimate answer to whether life sparked in the cosmic dawn may not come from a single telescope, but from a symphony of data, a convergence of evidence from space-based observatories, ground-based behemoths, and perhaps one day, an intrepid robotic scout sent to a neighboring star. The search is evolving from a question of if to a mission of when and where we will finally find the others. So we arrive at a breathtaking conclusion. Our journey began in a featureless fireball, a singularity of infinite heat and density. From that first moment, the universe expanded and cooled, forging the first atoms in its initial minutes. Gravity sculpted the dark ages into the first brilliant stars, whose spectacular death seeded the cosmos with the very elements of life. Within a few 100 million years, the first rocky planets coalesced from this stardust, bathed in the universal warmth of creation's fading echo. The chemistry for life was likely already brewing in interstellar space, and the potential for that chemistry to awaken into biology existed almost immediately. This entire cosmic metamorphosis, from a formless beginning to a universe potentially teeming with living worlds, may have occurred in less than 1 billion years. The timeline is so compressed it redefines our place in the story. We are not latecomers to a vast, ancient, and empty stage. We may be living in a universe that has been biologically active for nearly its entire existence, a cosmos where life is not a rare accident but a fundamental and swift outcome of its very laws. This realization transforms the night sky. Every star you see is not just a distant sun. It is a historical marker, a point of light from a past that might have witnessed the rise and fall of civilizations older than our planet. The darkness between them is not an empty void, but a living chronicle, a canvas that may have been painted with biology for over 13 billion years. Your task the next time you stand under that starry canopy is to see it with new eyes, look up and perceive not a still image, but a dynamic, unfolding biography of a universe that might have been alive from its very first breath. Let that profound wonder fuel your curiosity, for we are only just beginning to read its opening chapters.